A good framework for considering stars is cosmic chemistry. Just look at the difference in the composition between our sun, the star we orbit, our bodies, and the Earth we stand on. These have quite different abundances of their most common elements. If we sampled a typical region of the sun, we'd find that 90% of the atoms would be hydrogen, nearly 10% helium, and less than 1% all other elements taken together. Carbon, nitrogen, and oxygen are rare, and the metals fantastically rare in the sun compared to hydrogen and helium. Humans, by contrast, are clearly not made fundamentally of star stuff. The two most common elements are hydrogen and oxygen in the ratio 2:1, reflecting the fact that humans are 65% water. In fact, all living creatures are made of water as a primary component, ranging from the low 30% for beetles and dry bugs up to 99% for jellyfish. So hydrogen and oxygen in this proportion are present in all living creatures. The third most abundant element in living material, biological material, is carbon at just over 10%. Nitrogen is also quite abundant, and then all other elements are quite rare, far less than 1%. Different composition again is seen in the planet we stand on. Oxygen and silicon are the most abundant ingredients, followed by iron, nickel, and other heavy elements. These are the materials in rocks that we find under our feet, carbonates and silicates for the most part. The story of these different environments, the environment of stars, of which the sun is a typical example made mostly of hydrogen and helium, of biological material with large concentrations of carbon, nitrogen, and oxygen, and terrestrial material, which also has large amounts of heavy elements and also metals, is a story of cosmic chemistry. In particular, carbon, nitrogen, and oxygen, the biogenic elements, are enhanced by factors of hundreds relative to star stuff. Without that enhancement and that concentration at our position in the solar system, life would not be possible. One of the most fundamental diagrams in science to be able to explain is a plot of the cosmic abundance of the elements of the periodic table in increasing atomic number. Such a graph shows characteristic features and patterns that need to be explained, and they were indeed explained in the last half century using principles of stellar astrophysics. The first noticeable feature is the dominance of hydrogen and helium, followed by an extremely low trough where boron, lithium, and beryllium, light elements, are incredibly rare. There's a secondary peak at carbon, nitrogen, and oxygen, and a steady fall-off with a third peak at iron. Beyond iron, the heavy elements are incredibly rare. In a logarithmic plot, we tend to overlook the fact that they're thousands or even millions of times rarer than the biological materials carbon, nitrogen, and oxygen. Another omnipresent feature of this graph is the sawtooth pattern, whereby atomic numbers that are even have slightly higher abundance than their odd-numbered neighbors. What causes these patterns? What explains the cosmic abundance of elements? Explaining this is one of the fundamental things that astrophysics can do and has done in the past few decades. The origin of the very lightest elements, hydrogen and helium, is actually a story of cosmology to be told later. Helium and other very light elements were produced in the Big Bang when the entire universe was the temperature of the core of the sun. This was a transient state, only lasting a couple of minutes, but it turns out that nearly a quarter of the mass of the universe is produced into helium by the Big Bang itself in nucleosynthesis early in the history of the universe, 13.7 billion years ago. This is an extraordinary event. If it hadn't happened, we wouldn't be there to talk about it. In fact, if the universe had expanded much faster or much slower than it did early on, these heavy elements would not have been created because stars would not have had the ability to form out of condensing gas. As we move into the realm of stars, we move beyond the realm of direct experience. Humans have set foot on just one celestial object beyond the Earth, and that's our near neighbor, the Moon, just 250,000 miles away. Through our robotic emissaries, we have remote sensing covering roughly 1 billion miles into the outer solar system. We've soft landed, for example, on Saturn's moon Titan. This gives us fairly direct information on planets and moons in the solar system. We also sometimes get lucky and have free samples landing on Earth from the more distant regions of the solar system, extending perhaps to 10 billion miles. But that's the limit of our direct evidence, evidence where we can inspect matter up close. For the entire rest of the universe, the entire realm of the stars in the Milky Way and all the galaxies beyond, we have to rely on electromagnetic radiation in its various forms. Essentially, for 99.99999, etc. % of the universe, our information is indirect. purely in the form of electromagnetic radiation. That limits the inference we can make about distant regions of the universe. The story of stars is a story of cosmic chemistry. If we look at the difference in the chemical abundances of elements in humans or any living creatures, the Earth and the Sun, we see strong differences. Most of the universe is hydrogen and helium, with relatively small amounts of heavier elements. The fundamental diagram we're seeking to explain is the cosmic abundance of elements through the periodic table as found in space. This diagram shows distinctive features that can be understood in terms of stellar evolution.